So this is the second part of the video of Iiser Kolkata MSc entrance test exam. Okay, so in the last video I have already solved the problems coming from algebra section. In this video I am going to solve the rest of the problems, which is a part of mainly analysis. Okay, so the question number 10, that is the continuation of the first part. It was 9 questions. Okay, and all the questions are from algebra, and this section is from analysis. So question number 10 says that let n be a sequence defined by n equal to n for n belongs to 3, 6, 9, for that n equal to n square sine 1 by n when n belongs to 1, 4, these, and n equal to n sine 1 by n plus sine n when n belongs to 2, 5, 8, this thing, right? First observe that we know limit x goes to 0 sin x by x is 1, right? So in particular, for limit I can take a sequence 1 by n and limit n sine 1 by n equal to 1 as n goes to infinity. Now if you have a convergence sequence, then any subsequence must be convergent, right? Now let ank, okay, nk sine 1 upon nk, where nk goes to this subsequence, okay, say 2, 5, 8, say so on. Then ank also converges to infinity, okay, and sine 1 by n, sine n is bounded by 1. So in particular, is a bounded sequence, right? Then by Bolzano-Weierstrass theorem, convergent subsequence. Now see, if you see the definition of an, n sine 1 by n plus sine n, this is already a subsequence of an, and since this subsequence is bounded, it has a convergent subsequence, right? Now subsequence itself is a subsequence of an. So in particular, you can consider that subsequence to be a subsequence of an and say that that subsequence is convergent by using Bolzano-Weierstrass theorem. Hence we are able to show that an has a convergent subsequence. Go to the next one. Let p be a non-constant polynomial. Show that limit mod x tends to infinity, mod px equal to infinity. Okay, so we need to use reverse inequality here, reverse triangle inequality. Okay, reverse triangle inequality. What is that? This one. Okay, let px equal to an x to the n plus an minus x to the n minus 1 plus a0 with n not equal to 0. Okay, then mod px equal to mod an x to the n plus an minus x to the n minus 1 is greater equal to mod an mod x power n. Okay, or I think it is better to write okay. Right, px is greater equal to this, right? Now what you can see, px now, as we can see, say this one is this two, this, it is just a manipulation of inequality, nothing else. You can do it in different way also, like how do you use the how do you use the uh, like what should I say, how do you use the inequality, that is important here, nothing else. So it's not a big issue. Okay, so this is happening now. As mod x tends to infinity, these all terms goes to 0 because this term is a n minus 2 by x power n minus 2, so by x, sorry, because this is by x and so on, right? So as mod x tends to 0, this part plus 2x plus a0 by x power n minus 1, this part goes to infinity, sorry, this part goes to sorry, this part, as as mod x tends to infinity, this part goes to a n minus 1. Okay, and this part is non-zero and this part is goes to infinity. So in particular if you take limit on both sides, px equal to infinity as this goes to infinity. Because this section goes to 0, right? Except this part, all this section goes to 0 at mod x tends to infinity. So this section goes to an minus 1, and then definitely this section goes to infinity as n tends to infinity, and sorry, as mod x tends to infinity. N is a fixed degree here. Now you can do it by epsilon delta argument also, or you can do by using that px is order of the order of x to the n. So you can do that in that way also, but ultimately all the arguments are same. So this is the thing. Okay, and go to the next part. That the next part says that we need to show by using this. So hence, so we can think P from R to R be a continuous map using this polynomial. Okay, so as mod x tends to infinity implies mod px tends to infinity. Okay, inverse image of bounded set is bounded, right? And due to continuity, inverse image of closed set is closed. This will imply P inverse 1 comma this is closed and bounded. Hence compact. Okay, so since as mod x tends to infinity, mod px goes to infinity, so inverse image of bounded set is bounded, and due to continuity we know that inverse image of closed set is closed. So hence P inverse closed interval 1 comma 2 is bounded and closed, hence compact. Show that the series summation 1 by n sin x by n converges uniformly on 0 1. So by Weierstrass M test, mod of 1 by n sin x by n is less equal to 1 by n square for x belongs to 0 1. Right? So hence by M test, summation 1 by n square is convergent, hence summation 1 by n sin x by n convergent absolutely is uniformly convergent. Uniformly convergent on 0 1. Part B. Verify the uniform convergence of f n x equal to x to the n by 1 plus x to the n on 0 infinity, I think. Let me check. We have defined a sequence of functions, so we need to define the domain also, that on which it is defined. Let me check. I forgot to write it. So yeah, on 0 infinity. So verify the uniform convergence of f n x equal to x to the n by 1 by x squared n. Okay, I think here I don't have page, so I have to use some new page. It is better. So let f n x equal to x to the n by 1 plus x to the n. So if x equal to 0, then clearly f n x equal to 0 for all x. Sorry, for all n. If x not equal to 0, then f n x equal to 1 by 1 plus 1 by x to the n Okay, so then what? X not equal to 0, then x 1 by x to the n, right? Now if x greater than 1, okay, then 1 by x less than 1, then 1 by x to the n tends to 0 as n tends to infinity. So, and if x less than 1, okay, then x to the n tends to 0 as n tends to infinity. So ultimately, finally, we have the limit function to be fx equal to 0 if x belongs to closed interval 0 to open interval 1, and fx equal to 1 if x equal to x greater equal to 1, right? Now you can use directly a result that we know uniform limit of sequence of continuous function is continuous, but here the limit function is discontinuous, hence the convergence is not uniform. But if you do not want to use it, you can just do the definition. Okay, so define a sequence mn. We know the mn test. Supremum x belongs to 0 infinity mod fnx minus fx equal to mn equal to supremum of x belongs to 0 infinity x to the n plus x to the n minus fx. Okay, so I need to divide two part, because fx limit function fx is defined in two different way. So equal to supremum x belongs to, say, I'm defining it, I need to take both the maximum of these two value. Okay, max equal to max of supremum of this x power n plus 1 by x power n minus 0 and supremum of x belongs to 1 to infinity x power n 1 plus x to power n minus 1. Okay, which is same as maximum of supremum of x belongs to 0 1 and this x power n by 1 plus x power n. Okay, for any n mn, this supremum value becomes 1, because as x tends to 1, this becomes half, not 1, this becomes half, and yeah, so so x by 1 plus x, right? So it is half, and here it is n 1 by 1 plus x to the n. Supremum value is half, so mn tends to half as n tends to infinity, since because this supremum value goes to half actually at x equal to near about x equal to 1. For x equal to 1, here it is 1 by 2, and as x tends to 1, it is also 1 by 2. So mn goes to 1. So, and since mn doesn't converges to 0, this implies that the convergence is not uniform. It's not uniform. Okay. Go to the next one. That show that the function fx equal to sine root x. uniformly continuous on 0 infinity. So first observe that on any closed plus bounded interval, continuous implies uniformly continuous. That means, so sine root x, this is continuous on 0 infinity. That is no doubt, right? That is by definition. Composition of two continuous function. Now, if you take any closed bounded interval, say 0 comma a, so that means on 0 comma a, f is uniformly continuous, right? So if f is not uniformly continuous on 0 to infinity, that means it is only possible that this function's uniform continuity breaks when for large value of x, right? That means as x goes to infinity, because on closed and bounded interval, this is uniformly continuous, right? So only case when uniform continuity can break, that is as x goes to infinity, right? So, but you can prove it by using epsilon delta concept. Okay, so let me prove that. So observe on 0 1 f is uniformly continuous, right? And again, sin x is differentiable on open 0 infinity, sin root x, right? So you can write it as sin root x minus sin root y as less equal to cos, like, sorry, and write that sin root x minus sin root y is cos root c by 2 root c times x minus y. So by taking mod, this becomes this, which is same as 1 by 2 times x minus y if xy both greater or equal to 1, right? So on closed interval 0 comma 1, f is already uniformly continuous, and sin root x minus sin root y uh, less equal to half times x minus y if xy greater or equal to 1. So now let epsilon greater than 0 is given. Okay, I need to choose an uniform delta that will work for any x and y, right? So choose delta equal to epsilon by 2. Okay, so then mod x minus y less than delta implies half times x minus y less than epsilon by 4. That will imply that sin root x minus sin root y less than epsilon by 4, which is less than epsilon, right? And again, on 0 1, delta implies x minus fy less than epsilon. Now let x belongs to 0 1 and y belongs to 1 to infinity. Okay, so here the first case both x and y belongs to like both x and y belongs to closed interval 1 to infinity. Here both x and y belongs to closed interval 0 comma 1, and here one belongs to 0 comma 1 and another one belongs to 1 to infinity. Then what will happen? Then mod fx minus fy, it is less equal to mod fx minus f1 plus mod f1 minus fx, sorry, fy. Now from this part we'll have epsilon by 2, right? And for this part you have epsilon by 4. So ultimately you have less than epsilon. So hence for the all the three cases we have shown that we can choose an uniform delta which is epsilon by 2 such that this holds. Okay, hence this one is uniformly continuous. This implies f is uniformly continuous. Now the last problem. So if closed interval ab to r be a non-negative Riemann integrable function such that integration a to b f equal to 0. Show that f is 0 at each point of its continuity, right? So without loss of generality, I assume that f is continuous at some interior point. So if f is continuous at a and f is continuous at b, you can show in same way. Okay, so let b belongs to ab, okay, and f is continuous at b. And for any epsilon greater than 0, there exists a delta greater than 0 such that mod fx minus fp is less than epsilon whenever mod x minus p less than delta. Now integration a to b f equal to integration a to p minus delta f plus it, p minus delta to p plus delta f plus p plus delta to b f, right? So the actual integration is 0 and f is non-negative. Since f is non-negative, this will imply the integration p minus delta to p plus delta f is also 0, right? F is also 0. Now by given condition, whenever x belongs to p minus delta to p plus delta, fx belongs to fp minus epsilon to fp plus epsilon, right? And by definition of integrability, p minus delta plus p plus delta fx dx is greater or equal to p minus delta to p plus delta fp minus epsilon times dx, which is same as fp minus epsilon times 2 delta, right? P minus epsilon times 2 delta. So this is the quantity. So integration p minus delta p to p plus delta fx dx is greater or equal to fp minus epsilon times 2 delta, right? Now choose sufficiently small epsilon greater than 0 such that fp minus epsilon, this is greater than 0, right? Okay, okay. I can choose that sufficiently small epsilon because fp is non-negative, it is non-negative. So itself, if fp is 0, then we are done by given condition. But if fp is non-zero, then we can choose sufficiently small epsilon such that fp is greater than epsilon, right? Because epsilon is, we can choose any epsilon and then we can find some delta here and we can choose that delta here in our condition case, right? So if fp is itself 0, then we are done, because we need to show that fp has to be 0. But if fp is already 0, there is nothing to show. But if fp is non-zero, then we can choose a sufficiently small epsilon such that fp minus epsilon is greater than 0. So that will imply that integration p minus delta to p plus delta f is strictly greater than 0, which is a contradiction, because from our given condition we know that this has to satisfy this condition, but by definition of integrability we get that this is greater than 0. Hence fp has to be 0 at each point of continuity. Okay, now what about the second part? So the second part says that what about the point of discontinuity? So consider a function, say fx equal to 0 on, say, so on closed interval 0 on fx equal to 0 for x not equal to half, and 1 for x equal to half. Okay, 0 for on x not equal to half and 1 for x equal to half. Then if you do the integration a to b fx dx, by the way, if the continuity, you need to show the continuity at a and b, then you can do the same thing, but here you have to start from a to a plus delta for checking continuity at a, and in that case instead of 2 delta there will be delta only, but the everything will be same. And for b to b minus delta, here you have to do b minus delta to b, and there you have to also, you will have delta also. Other things are same. Okay, so the idea is actually same. So integration fx dx is 0, but f is not equal to 0 at x equal to half, which is the point of discontinuity. And why for this function integration is 0? That is the common definition, that is the usual definition of upper Riemann sum and lower Riemann sum. You can take the partition and you can do you can take a neighborhood of 1 and you can squeeze it as small as you can. So the upper Riemann sum and lower Riemann sum is already 0, you can easily see, or lower Darboux sum, what you can say, both are equivalent definition. And if you do the upper Darboux sum, you can see that you can take the interval to be so small so that it goes to 0. So when you are taking the finer and finer partition, you can say that the supremum of that value will be 0. So that is the idea. So the upper Darboux sum and lower Darboux sum are same and both are 0, so integral value is 0. Okay, but f is non-zero at the point of x equal to half, which is the point of discontinuity here. Okay, that's the entire solution.